A linear algebraic toolbox for analyzing strongly connected components. Is author of the paper is Professor Reggie Davidrajuh at University of Stavanger. Strongly connected components SCC. Strongly connected components of a directed graph is group of vertices in which each vertex source has a path to other vertices and the path leads back to the source vertex. Two or more strongly connected components can be merged into one by injecting one or more edges. Also, by removing an inner edge, strongly connected component can be split into multiple strongly connected components. Traditionally, graph theories or graph transversal algorithm are used for analyzing strongly connected component as a graph. Graph traversal algorithms are usually efficient, taking polynomial running times, linear or quadratic. However, traversal algorithms are not for parallel computing and linear algebra techniques. This paper presents linear algebra technique, toolbox, MATLAB functions for analyzing strongly connected components. These functions are efficient, easy to understand, and simple enough to implement and extend it. Strongly connected component, there are three components. 1, 2, 3. V7, V5, V6, V1, V2, V3, V4. How do we find the strongly connected components? By Tarjon's algorithm that involves two depth first search DFS, taking time O V plus E time. Reachability matrix R. Reachability matrix R is identity matrix UA, UA square, UA cube, and so on. A is adjacent matrix. E is the total number of edges. I the identity matrix. And U is the logical OR operator. R represents the possibility of starting from one vertex and reaching other vertices in any number of steps. Radar's method. Radar's method provides a shortcut for R. Let alpha be a small value, e.g. alpha is equal to 0.5 and I be the identity matrix. Radar's matrix Q is given by the following equation. Q is equal to identity matrix minus alpha time A adjacent matrix inverse. Q would possess exactly the same non-zero elements as in the reachability matrix R. Hence, strongly connected components is equal to R time R and R transpose is equal to Q and Q transpose. Component matrix. By combining radar's matrix Q and Q transpose, we get the connection matrix Cn. Purging duplicate rows in C and gives the component matrix as this. So component matrix shows the one component per row. Component 1, component 2, component 3, and so on. Intercomponent link ICL. ICL, this operator finds an edge V, I, Vj, STV, J belong to component identity and Vj component J, where component I is equal to component J. The example is given. Example for the ICLR V6, V7, V6, V7, V2, one component, V2, V7, V3, V3, V5, and V3 to V6. Intercomponent length ICL in matrix form V6, V7 from component 2 to component 1, V7, V2 to V7 from 3 to 1, V3, V5 from component 3 to component 2, and V3, V6 from 3 to 2. And then the ICL matrix is in this form. Merging two strongly connected components. ICL play a major role when merging two components together. Example, to merge component 2 and 3. ICL show the component 3 is linked to component 2 in one way direction only, V3 to V5 and V3 to V6. So a simple way of merging two component and three component is to choose one of the link V3 to V5 or V3 to V6 and make it bidirectional. Splitting an SCC. Split a strongly connected component into a number of smaller strongly connected components. Either remove an edge inside, or if the edge is bidirectional, will make it one directional. Note that many components could emerge by removing a single edge. For example, if the edge Vn to V1 is removed, making it one directional, then n components will result. Main function of the linear algebraic tool for component analysis. We have the function and the purpose. Conclusion, application of the toolbox. The toolbox is an addendum to the tool generation general purpose PatriNet simulation. GPensim is also developed by the author of this paper. GPensim is used for modern simulation and performance analysis of discrete systems. Some applications also use GPensim for developing distributed cyber modules known as Petri modules of large industrial discrete systems. In this case, the cyber module must be of optimal size, neither too large nor too small. Intermodular communication takes too much time. Also, the cyber modules are usually strongly connected components of patterned elements. Hence, designers need to fine tune size of the cyber module so that it's not too large. Split the large strongly connected components in this place are not too small. Merge smaller strongly connected components into one, making use of the functions discussed in this paper. Thanks for listening.